Okay, hello and welcome back to Chemistry Talk. Today, we'll be talking about acids and bases, continuing our discussion of the concepts, and we'll discuss the chemical definitions of acids and bases. And there's three main ones that you have: the Arrhenius, the Bronsted Lowry, and the Lewis definition. Very important stuff. So, the Arrhenius definition of the acids and bases is the first one that we have back to date, and it's not really used as much anymore because it only relates to water reactions that occur in water. However, you do need to know it, and the Arrhenius definition of an acid is that it's going to release a hydrogen ion, and a base is going to release a hydroxide ion. So here you're seeing the dissociation of a strong acid and a strong base. The hydrochloric acid dissociates into hydrogen ions and chlorine ions. It releases that hydrogen ion, and the strong base releases the hydroxide ion. So that's all the Arrhenius definition says. The more important definition that is used a lot is the Bronsted-Lowry definition. Now, Bronsted was one person, he was a Swedish person, and Lowry was another person. And their works were combined in the early 1900s to have this modern definition of an acid and base. And what it really says is that an acid is a proton donor and a base is a proton acceptor. So in a given reaction, in an acid-base reaction rather, you're going to have a substance that's going to release a proton. That's going to be the acid. And the thing that accepts the proton is going to be the base. So per the Bronsted-Lowry definition of an acid and base, an acid must have a removable proton that it can transfer and donate, and a base has to have a non-bonding electron so that it can accept the proton. So in this reaction, it's a strong acid with water. So it's the dissociation of a strong acid. I didn't have to include water, and I could have just gotten the hydrogen ion here, but I decided to include water, so I get the hydronium ion, which is the same thing. And as here, the hydrochloric acid's donating the proton, so it's acting as the acid. But the water is accepting the proton. The water is going from H2O to H3O plus. It gained a proton, so it's acting as the base. Now, there's one more definition. After Bronsted-Lowry's were replaced by the Arrhenius definition, there was another one that came about. Now, this is the Lewis definition, which doesn't require an aqueous environment or an exchange of hydrogen. So the Arrhenius definition requires that you be in an aqueous solution of water. The Bronsted-Lowry requires that you have hydrogen ions. Now, the Lewis definition doesn't require either of those things, so it is the most broad. The Arrhenius is the most specific, the Bronsted-Lowry is in the middle, and the Lewis definition is the most broad. Now, Lewis acids are electron pair acceptors, meaning they want to accept an electron, they want to become more negative to get to a full octet. While Lewis bases want to donate protons, they want to, Lewis bases want to donate electrons. They want to lose a negative charge to become more positive. So anything that could be a Bronsted-Lowry base or acid is a Lewis base. So I just have a couple of questions here, just reviewing the definition. So here it says a Bronsted-Lowry base is defined as a substance. Okay, well, a Bronsted-Lowry base is going to act as a proton acceptor. It wants to accept a proton, so this would be D here, because the Bronsted-Lowry base accepts the proton. The Bronsted-Lowry acid donates the proton. So here, a Bronsted-Lowry acid is defined as a substance that is going to donate a proton. All this stuff about hydrogen ion concentration and hydroxide ion concentration does not have to do with definitions of acids and bases with the Bronsted-Lowry. The Bronsted-Lowry acid, it donates the proton, it loses the positive charge, which is usually the hydrogen ion, and the Bronsted-Lowry base accepts that proton. According to the Arrhenius concept, okay, so this is the first definition of an acid and base, which is the following is true. Well, the Arrhenius definition says that an acid is going to lose hydrogen ions in concentration. So remember, we had the example of the hydrochloric acid. And when you dissociate hydrochloric acid into water, you're going to get a hydrogen ion and a chlorine ion. So the Arrhenius definition says that when you dissociate an acid in water, you're going to get an increase in the hydrogen ion concentration. So looking here, this would be B. The Arrhenius acid causes an increase in the concentration of hydrogen ions because when you're dissociating an acid, per the Arrhenius, you're going to get hydrogen ions. This is for strong acids. You're going to get hydrogen ions, and that is the definition of the Arrhenius acid and base. But like I said, this one is not used as much as the Bronsted Lowry. All right, so this is an important problem here. According to the following reaction, which molecule is acting as an acid? So what we haven't talked about yet is acid and base conjugate pairs. Every acid has a conjugate acid, every base has a conjugate base. But we're just going to look here for which molecule is donating the proton, because the acid donates protons, or donates hydrogen, whatever you want to think of it, but it donates the proton, according to Bronsted-Lowry. So which of the following substances here on the reactant side is going to donate a proton? Well, here we have water, and here we have hydronium. So the water accepted the proton. So here the water is the base. So it can't be these two. But the sulfuric acid here is donating a proton to form HSO4 here. So what's happened is the HSO4 has accepted the proton, and the sulfuric acid has donated it. So the answer here would be A, the sulfuric acid, because it's losing that proton to become HSO4. So it's acting as a proton donor. So therefore it's the acid in this problem. Its conjugate base would be the hydronium ion, and the water's conjugate acid would be the sulfuric. Okay, last question. Which of the following ions is the strongest Lewis acid? Well, the Lewis acids want to accept electrons, because when you're mixing them in an aqueous solution of water, you want to have something that accepts the electron from the water. So which of the following is most likely to accept an electron? Well, the ion that's going to accept the electron is going to be the ion that's most positive. And here the ion that's most positive is the aluminum ion. Because it's the most positive, it's going to want to accept the electron and become the Lewis acid. So I hope this helped you to understand the definitions of acids and bases, the Bronsted-Lowry, the Arrhenius, and the Lewis. In future videos, we'll be getting into the math of acids and bases. Be sure to subscribe and comment.